Okay, good morning, good afternoon, whenever you're tuning in. If you missed 8.12 on the product rule, or you wanted a second go at it, here's your chance, here's your video. First, I talked about different types of functions. All of these we can see have trig in them and have something else combined with them. And I wanted to really demonstrate how I would organize my thought and how I would separate how these look and then how they're solved in order to, not solved, but taking the derivative of these functions. So this very first one, we can see why 5 minus sine x. For this one, we can see that we have two terms, right? Two different things, a 5 and a negative sine x. Those are separate, and they're separated by that minus sign. So that minus sign, or if there was a plus sign there, separates or cuts things into basically two distinct functions. So those are two terms. And how we do those, remember, is that we take the derivative of each term separately. So if we wanted to take the derivative of this function y to get y prime, we would first take the derivative of 5. And remember that since that's a constant, our derivative is going to be 0. And then I'm going to actually just copy that minus sign down. I'm going to think of that as like a coefficient up front. And I'm just going to take the derivative of sine. And I know that the derivative of sine is cosine. So I have 5 minus the derivative of sine. I've taken the derivative separately. Now I'm just going to put them back together. 0 minus cosine x is just negative cosine x. So once again, two separate terms, do the derivatives separately. Number 2, or maybe we can call this, that was A and this is B. Part B here, we can see that, okay, that is one term. And that term now has a coefficient. So even though that still has a number, it's not separated. Those are together. They're being multiplied. And that is a coefficient, which is a very important distinction. So how do we do that? Well, remember that with derivatives, we can leave that coefficient alone and just take the derivative of the rest and then put that derivative back on at the end. So how we would do that is something like this. Okay, let's leave the coefficient of 3. And now let's take the derivative of sine. The derivative of sine, if we use our reference chart, is going to be cosine. Now there's nothing to simplify here, combine or anything. So this would actually be our derivative. So in one case, if we have two terms, we take them separately. But if there's a coefficient, we leave it and we take the derivative of the rest, put that coefficient back on. If there's anything to multiply, I would, but there's nothing. And now for this last one, you might be thinking, what do I do? That's a 4x and it kind of looks like a coefficient, but it kind of looks like something different. Here's how I want you to think about that. I want you to think about this as being one term, but it is the product of two functions. So it's the product, the multiplication, right? There's no time sign there, but we know it's being multiplied, of two functions, right? I would think of that 4x as being its own function and sine x being its own function. I can actually take the derivative of each one of those. So how do I do that? Well, this is what we're going to talk about today. There's a new method, and that's called the product rule. And there's a formula that is associated with something specifically related to this, we'll call this type C problem. When we have one term that is the product of two different functions, we have to have a different approach. And what we're going to do is we're going to talk about what that approach is, and then we'll talk about the why that approach matters. So kind of flipping the why and saving that until the end. So let's actually go and do an example of one. Here's one. We actually can see here that we have the product of two different functions. We can see that these two things are being multiplied together. And what I mean by these two things, I have f of x, 2x plus 1, and an x minus 3. We're trying to find the derivative. I have two things being multiplied together, each one of those being kind of its own individual function that I can take the derivative of. We'll call this one u, and we'll call this one v. And so if I have two things, u and v, being multiplied together, and it's not like a coefficient, then what I'm going to do is I'm going to use this formula, which is the product rule formula. And now we did a similar type of formula with the quotient rule. I know most people would do the product rule first. And when I did this, I actually set up a chart for myself with u and v and u prime and v prime, and I actually figured out what all of those four things were first before I plugged it into this formula. Well, u is just going to be whatever is, the first function that is being multiplied, and v I would just kind of consider to be the second function. And now while that order doesn't matter with the u and v order doesn't matter with the product rule, I would continue to use this rule because it's so similar to the quotient rule where it does matter. Now I'm going to take the derivative. The derivative of 2x, that linear function, is 2. Remember, the derivative of constant is 0. So I'm not going to put 2 plus 0, just 2. The derivative of 1x, since that's linear, is just 1, and negative 3 is 0. So now I have all of my u's and v's and u primes and v primes, and now I can put that all into the correct order. Now we're trying to find f prime. Okay, so let's try to put this in the correct order. We're going to go first from u prime times v. So u prime times v. So I'm going to use parentheses to show that, u prime times v. And then we're always going to put that plus sign in there. And then we're going to go to, let's see, we got to go to u times v prime. So there's u times v prime. Now, while this is the derivative, we know that this isn't cleaned up all the way. We can see that we have all these parentheses in there, which is showing us a separation of terms. But we can put some terms together and actually multiply and combine some things. So let's see. Let's distribute 2 times x and 2 times negative 3 gives me 2x minus 6. And we'll put that in parentheses because then we're going to add, let's see, 1 times both of those, which is going to give us 2x plus 1. And really, I'd be distributing a positive 1 onto the inside. Why I'm taking the time to do that is because if that were a minus sign in between, that's going to change some things. But in this case, we just have this 2x minus 6 plus 2x plus 1. And of course, this is just me continuing to rewrite and clean this up using my old algebra skills with distributing and now combining my like terms. I got 2x and 2x, which is 4x. Negative 6 and plus 1 is going to be a negative 5. And there's my derivative. So this was my derivative using the product rule. And we're done with this problem. Now what I'm going to do is I'm going to save all of this work here. We've done this derivative, and I'm going to talk about why this derivative and why we need this specific rule in order to do a problem like this. So let me just erase some of my scrap work off to the side here, which was necessary to do this problem, but I'm really just going to concern myself with the answer for this next step. And now when I'm looking here, I'm going to say, okay, let's go back to why this is necessary. Because some people, and this is just kind of going to be like a test, right? Does it, maybe I had like a guess of how to do this problem to start. Some people might say, okay, if my original function was f, right, and I had 2x plus 1 and x minus 3, maybe what I would try to do is like, okay, maybe I'm going to try to see if f prime is equal to, let's see, if I can just take the derivative, that would be 2, and if I take the derivative, that would just be 1. So is it true that I can just take the derivative of each one of those to actually get the derivative? Well, we found that that didn't work. But how can I prove that? How can I prove that this actually isn't the derivative? Right? How can I prove that this is incorrect? Because you might be thinking logically, yeah, if I want to find the derivative, just take those two derivatives and multiply them. It's kind of like order of operations, right? Why do I have to do all of this junk over here to arrive at this? Well, let me show you a quick little proof. Another way to think about this problem is to actually multiply these two things first, right? You might know the FOIL method, or you might know the box method in order to multiply binomials to get a polynomial. So this isn't u and v yet. This is just regular old algebra multiplication. And what I would get here is the following. And if I put that all together, what I've actually done is I've rewritten my original equation in expanded form, right? In standard expanded form. So if I were to highlight these two things, I started with this, right? Which is the same if I were to actually multiply that and expand it out as this. So if I take the derivative of that first one, I should also be able to take the derivative of this one and get the same thing. These two things are, once again, the same. So if I want to find the derivative of that, I could just find the derivative of this after multiplying. So let's actually do that. All right, now if I were to do this, I would just do the power rule. Remember, you move the 2 down to the front, multiply it, subtract 1, so it's 4x to the first. Negative 5x turns into negative 5 for this linear. And then remember that negative 3 is a constant, so that turns into 0. So this would be my y prime if I were to do it a little bit differently. And we can see here that these same two functions have the same derivative. That's kind of a proof here that we can't just take the derivative and multiply those two things. That won't work, that we need something, an extra little step here. So let's just kind of talk about why that is, or like just sum this up. Okay. So here are my thoughts and my kind of final thoughts on this. The product rule is used anytime I have two different functions being multiplied together. 2x plus 1 and x minus 3 are two different things being multiplied together. So I should use this formula. After I used that formula by setting up my table, I got this answer here. There's my derivative. Now, there is an alternate method, which I actually showed you off to the side, which what we could do is instead of taking the derivative of that from the start using the product rule is actually to multiply those two things together first, right? Use your box or FOIL method to change the way that looks. And then you can use your power rule from there. That's a way to kind of avoid your product rule. But that won't always be something that you can avoid. Sometimes you can avoid it, like in this problem where I can multiply and then take the derivative second. But let's take a look at one where I can't avoid using the product rule. I can't just use the power rule to get there, where I have to use this formula in order to get home to my answer. All right, let's take a look. Let's just give you one where it's just y equals 5x sine x. And in something like this, if I want to find y prime, I can see here that what I have is I have two distinct functions being multiplied together, 5x and sine x. I know that's not a coefficient because it's a 5x. So I'm going to call that u. I'm going to call it sine x v. And what I'm going to do is I'm going to set up my chart just like before. Separate example. I can't like multiply those out and take the derivative afterwards. I have to use the product rule. So I'm going to get 5x, which turns into 5. And I'm going to have a sine x, which turns into cosine x, right? If I take the derivative. And now it's just putting that in the correct order according to this formula. So we're going to get y prime equals, let's see, u prime times v is 5 times sine x plus, because of that plus sign that is always in that formula, u times v prime, so 5x times cosine x. I'm putting those parentheses to show separation and to show my multiplication. And now I can actually put some things together. Let's see, 5 times sine x, I would just call that 5 sine x. Some students might think, well, that x times that x is x squared, but that x actually is inside with the cosine. So I'm really just going to leave that 5x times cosine x as two kind of different functions being multiplied together. And that would be my derivative. Okay. So in the previous problem, I could have used the product rule, or I could have expanded and then used the power rule. But in problems like this, I really have to use the product rule. There's no other way around it. I really, really have to use the product rule in order to find my derivative in something like this. All right, once again, why? Well, I got two functions being multiplied together. That's what the product rule is used for. That was why it was designed, and that's product, and there's like a really heady proof of it, but you just have to trust that it'll always work for these kind of scenarios when we are multiplying two distinct functions together. Anyhow, that's kind of a reteach of what we talked about today. Go try that exit ticket.